All right, let's talk about the invisible glue that holds so much of our world together. We're diving into the story of covalent bonds. It's all about how atoms decide to team up and share. Now, to really get what sharing is about, it helps to look at the opposite. Think of an ionic bond like a simple transaction. One atom just gives an electron away and another one takes it. Clean and simple. But a covalent bond, that's a partnership. It's two atoms coming together and agreeing to share their electrons, forming a real molecular team. And this one idea, sharing, is honestly one of the most powerful concepts in all of chemistry. So let's start with the best case scenario, the perfect partnership. And to do that, we're going to look at the simplest molecule out there, hydrogen gas, H2. It's the perfect example of why sharing is just so much better for these atoms. Okay, picture this. Two individual hydrogen atoms just floating around by themselves. They're kind of jittery, unstable. They've got all this high potential energy. See, each one has one electron, but what it really wants is to have two, to feel complete, like the noble gas helium. So on their own, they're just not happy. But then they start to get closer to each other. Their electron clouds overlap, and suddenly something amazing happens. Each electron isn't just attracted to its own nucleus anymore. It's attracted to the other nucleus too. This mutual attraction pulls them in, they share those two electrons, and bam, a covalent bond is formed. The whole system just relaxes into a much more stable, lower energy state. It's a total win-win. And when I say more stable, I'm not just speaking vaguely. We can measure this. When just 1 mole of these hydrogen molecules forms, a whopping 436 kilojoules of energy are released. That is a ton of energy, and it just goes to show how much these atoms prefer being bonded together. So the key idea here? Forming bonds releases energy, and that's what creates stability. This perfect situation, what we've just described, it has a name. We call it a pure covalent bond. And it makes sense, right? Since both hydrogen atoms are identical, they pull on those shared electrons with the exact same strength. The sharing is perfectly equal, a 50-50 split. That's the definition of a pure covalent bond. But, life isn't always a perfect 50-50 split. What happens when the partners in the bond aren't identical? What if one atom pulls on those electrons a lot harder than the other? Well, things get a little more interesting. So let's check out a new molecule, hydrogen chloride, HCl. Again, we've got two different atoms sharing a pair of electrons. But this time, it is not an equal partnership. Chlorine, you see, is a bit of an electron hog. It pulls those shared electrons much more strongly towards itself. It's really like a chemical tug-of-war. And in this matchup, chlorine is way stronger, so it pulls that rope of shared electrons over to its side. This means the electron cloud around the molecule gets all lopsided, with more electron density piled up on one end. So, how do we represent this imbalance? Well, chemists came up with a pretty clever notation. We use the Greek letter delta. The chlorine atom, since it's hoarding all that electron density, gets what we call a partial negative charge, or delta minus. And the poor hydrogen atom, which is now a little electron deficient, gets a partial positive charge, or delta plus. This separation of charge is the hallmark of what we call a polar covalent bond. Okay, so we get it. Some atoms pull harder. But how can we predict who's going to win this atomic tug-of-war before it even starts? We need a way to measure that pulling power. And luckily for us, chemists developed a crucial tool to do just that. And that tool is called electronegativity. You can basically think of it as a scale of atomic greediness. It's a number that tells us exactly how strongly an atom is going to attract electrons when it's in a bond. The higher the number, the stronger the pull. Simple as that. The scale was actually developed by the absolute legend of a chemist, Linus Pauling, who, by the way, is the only person to ever win 2 unshared Nobel Prizes. As he put it himself, he found a way to quantify this property, giving us an incredible tool to predict how electrons are going to be shared. And here's the best part. You don't have to memorize a bunch of random numbers. There's a beautiful, simple trend right on the periodic table. As you move from left to right across a row, electronegativity goes up. And as you move up a column, it goes up. This makes the elements in the top right corner the absolute heavyweights, with fluorine being the undisputed champion, the strongest, most electron-greedy atom there is. So, with these tools in hand, we can finally zoom out and see the big picture. We've got pure covalent bonds with equal sharing, and we've got polar covalent bonds with unequal sharing. And what this reveals is that chemical bonding isn't really an either-or choice. It's actually a continuous spectrum. And we can map out this whole spectrum just by looking at the difference in electronegativity between two atoms. We call it delta En. If that difference is really small, say less than about 0.4, the electrons are shared almost perfectly, and we call it a nonpolar covalent bond. As that difference gets bigger, the bond gets more and more polar. And if the difference is huge, something over 1.8, one atom pulls so hard it doesn't just hog the electrons, it rips them away completely, and that's no longer sharing, that's an ionic bond. And trust me, this isn't just some abstract theory. This is fundamental to life itself. Take a look at the common bonds inside amino acids, the building blocks of all proteins. A weakly polar CH bond behaves totally differently than a strongly polar OH bond. And it's these precise differences in polarity that allow proteins to fold into their incredibly complex functional shapes. It really all comes down to electronegativity. So let's just quickly recap the big ideas. Covalent bonds are all about atoms sharing electrons to get more stable. Sometimes that sharing is a perfect 50-50 split. That's a pure or nonpolar covalent bond. Other times it's unequal. That's a polar bond. The thing that decides all this is electronegativity, an atom's pulling power. And by comparing the electronegativity between two atoms, we can place any bond on that spectrum, from perfectly shared all the way to completely stolen. And that brings us to one last thing to chew on. We always see molecules drawn as these simple stick-and-ball models. But if bonding is really a spectrum, right? A dynamic tug-of-war with all these shades of gray between covalent and ionic, what does that say about what a molecule really is? It suggests a reality that's way more fluid, more complex, and honestly, a lot more beautiful than any simple drawing could ever show. Thanks for tuning in.